Okay, welcome to the last lecture of this class. So we'll wrap things up with a bit more of deep learning. This is barely enough to scratch the surface of what deep learning is. But I hope you'll get a little bit of an overview. There are plenty of pointers in the slides. The slides are up online as of yesterday, and the corresponding web page to that should be online as of sometime today. So we'll go through that. One quick thing, though. So next week, we will have project presentations, right? So that means that you should prepare your project, your slides, and there are instructions on Piazza of how to submit the slides, but basically make sure you have PDF versions of slides ready. The reason simply being that font compatibility between Keynote and PowerPoint and Mac and Windows, and even between Keynote and Keynote on different machines, is sometimes less than ideal. PDF has a lot less of that problem. Furthermore, since each presentation is only 5 minutes, we do not have enough time to actually go and set up everybody's laptop when they start, right? So this will all run off a single laptop, and the only way to make this work reasonably painlessly is to actually have all the PDFs on that laptop before. Okay. So there'll be a Dropbox link, and you can just dump things in there, which will make it a little bit easier if you have last-minute changes. But the only guarantee is that if you have it by Sunday, sometime noontime, we'll get that version in. If you make a last-minute change 5 minutes before the presentation, don't expect the Dropbox and me or any TA to sync their laptop 5 minutes before you're giving that presentation. Okay. So basically, get it ready by Sunday noon. Anything beyond that is bonus, right? You're lucky if it's in. If you are unlucky, it's not in. Okay. That's just a little bit as context. So, make sure you get things done in time. Okay, good. So what we're going to do today is we're going to look at objective functions of what we can actually optimize over, and then we'll look a little bit at optimization itself and memory. And in the end, there's one slide with toolkits and so on that might give you a bit of an idea of where this is all going. So to recap, what we had on Monday was a brief overview. We did backprop, and we basically looked at a number of layers. So if you think about it, layers are essentially the function classes, or at least the constituents of function classes. The objectives are, well, they start fairly mundane with classification and so on, and then sometimes all the key engineering is really in designing a nice objective such that you can optimize for the right thing. So it's not really the network that knows what it should learn. It's really the scientist that engineers the objective. So if you hear people talking about the network knows what it should learn, then they've probably had a beer too many or whatever. So the simplest thing is you could use it for classification, right? And we already did logistic regression. And logistic regression is kind of nice because it's continuously differentiable. So you can just minimize the negative log likelihood of seeing apples or oranges. If I have 1,000 classes, then that doesn't really change very much, except that now I have a softmax. We already did that before, but we just called it multinomial exponential model. Same thing as a softmax. So. Okay. The reason why it's called a softmax is because it gives you essentially the maximum of a set, except that it gives you a smooth version of the maximum of the set. As in, this operation here will give you a smooth version of the maximum, right? And you can change the smoothing by, for instance, having a coefficient lambda up here, and then you would have a 1 over lambda up front there. Does somebody have an idea what happens if I make lambda large? In other words, what happens if I make this lambda here larger? It's log of the sum of a couple of exponentials. What happens if I make lambda large? So I'm multiplying by lambda and I'm dividing on the outside, right? Okay. So what if I have log x of x? Well, if x is whatever, that will give me x back, right? Now, if I take the sum of a couple of exponentials, and one term is way larger than the others, right? Then the others won't really matter, right? So therefore, if I make lambda larger, I will make the discrepancy between the largest and the smallest terms even larger. And so, therefore, it's really only the largest term that matters. And then I divide here again. So what happens is that basically this will converge more and more to a simple max as opposed to a soft max. Okay. Question. Does this thing increase when I increase lambda, or does it decrease? Who thinks it increases with increasing lambda? Okay. Who thinks it decreases with increasing lambda? Okay, guys, this is about 10% of the audience. Okay, I'm not going to continue until I have a vote from everybody here. Who thinks it increases? Who thinks it decreases? Okay. It actually decreases with increasing lambda. Here's why. Basically, if I have, let's take the extreme case where lambda is very, very small, right? In this case, all terms are almost the same size. We know, therefore, that all the terms besides the largest term will contribute almost to the same extent as the largest term. And that's why it actually gets larger, right? So to draw the softmax, what you get is basically that this function here gets smoothed into this. And, well, the larger lambda, the smoother this becomes. Right. Okay, you can easily check that yourself. Okay, so you could use that. You could use any other objective that we've done in the past couple of months. It will be just fine. As a matter of fact, people do that. For instance, you can use least mean squares. You might have least mean squares not just over a scalar, but actually over vectorial data. Right? And so you can easily do that for stock market prediction. You can use it for image super resolution. Recommendations, ratings, any of those things would work just fine. Okay? I guess everybody by now knows least mean squares, so I don't have to belabor that in much detail. One of the reasons why least mean squares is nice is because its derivatives are so nice. So, well, the derivative with regard to yn is simply y minus yn. Right? So derivative with regard to y, actually. So this is very easy. So therefore, I can happily optimize over that. Okay, so now armed with those two things, I can already build something fairly interesting. So something that's called an autoencoder. And those things are often trained stage-wise. And they are trained stage-wise for a good reason, because we have a not so nice optimization problem. So if you think about it, let's just focus on the term on the left for the moment. Okay. So let's just focus on this term here. What we have is we have some input data x. And the idea is we have some mapping that maps x1 into x2, which is lower dimensional. And then we have a reverse mapping, let's say with some matrix V, that maps x2 back into something that is in the same space as x1. We might conveniently have some nonlinearities. Well, what's happening is, the idea is basically that I'm taking maybe an image, maybe text, whatever I might want to have, and I'm trying to map this into a lower dimensional space, namely the space x2, and then from that space, I'm trying to reconstruct again what the original sentence would have been. So a simple projection operation is just one of the simplest things that I could do. There are a lot of fancier things that I could use. So for instance, I could use a generative model, and we'll get to those a little bit later today. But basically, in trying to do this, the idea is obviously that the hope is that this compressed representation will capture the essence, if you will, of what x1 is really all about. But since you may only have a limited amount of nonlinearities, maybe 2 layers are better than 1. So what I could try is I could reduce this further, and I go therefore from x1 to x2 to x3, and then I unfold again. And this thing is called an autoencoder, because it tries to encode itself. We've actually seen those things before in the context of what's called a sufficient statistic. So if you remember, sufficient statistic of the data was this minimal sufficient statistic is a minimal representation of the data that contains everything about the data that there is to know about it. So, for instance, when we take images, when we take pictures on our cell phone, then the cell phone will go and compress things because you might have, a fancy 8 or 10 or 13 megapixel sensor, but the images are definitely not in the order of 30, 40 megabytes. They are probably in the order of maybe 1 megabyte, maybe 2. Now what happens there is we use JPEG compression to come up with a reduced representation of the original data such that we can then approximately reconstruct the original. And so you then not only need a mechanism of compressing things and decompressing, but you also need to have a mechanism of comparing what goes in and what comes out. And for a lot of vectorial data, well, a least mean squares distance is not a bad idea, under the assumption that the least mean squares distance will pretty well preserve the data that went in. Least mean squares on text is probably not so amazing because negative word counts don't really help. Right? Now, what you could do is, if you had, such a complicated system to train, because you're basically reducing dimensionality and then you're increasing it again, you could train it stage-wise, at least pre-train. So you could go and first train the first autoencoder, and then, with these parameters initially frozen, you could go and train that second autoencoder. That just takes care of this part. Then once you have all the parameters, you can happily jointly optimize over everything to do a bit more fine-tuning. So this stage-wise training is quite popular. So last year there was actually a NIPS paper on doing that very thing for image denoising and in-painting. They basically took image patches, ran them through an autoencoder, and tried to reconstruct them again. And then based on that, they managed to, learn what regular images without text look like. Then they took some images where text was on it, and lo and behold, it actually removed the text quite neatly without even knowing what text was. This is both a strength and also a downfall of this entire setup. The strength is that it is quite nice at removing extraneous things. The downfall is, if I take a picture of maybe some street scenes with house numbers and other things, it'll very nicely in-paint over the house numbers, and the houses don't have numbers anymore, right? So therefore, be careful what you wish for, or rather, what you train on, because that's exactly what you're going to get as your reconstruction. Right. So if I only train my autoencoder on forest scenes and then apply it to baby photos, we'll all get green Martian babies out of it. So don't do that. Yeah. So in other words, these things are highly distribution dependent. Any questions so far about the autoencoder? Well, there's one very simple case, namely PCA. Yes?
So you stated that the lower dimensional layer is auto reduced by why?
So first of all, in PCA we can see that immediately with all just linear terms. What you're basically trying to do is you're trying to get a projection from maybe a 1,000-dimensional space down to a 100-dimensional space, where then the linear up projection will recover at the best of your abilities that 1,000-dimensional space. So therefore, the 100-dimensional space is a bottleneck. Now, obviously, we're all good mathematicians, and we know that mathematicians can hide arbitrary information in a scalar, right? So if you don't know how to do that, a very simple way is you just have, let's say, 1,000 numbers. You write them in binary or floating point, doesn't really matter. You just take one digit each in round robin, and this way I can have a single floating point number that will contain all the information I can unpack just as well. Obviously, this only works if I don't have noise. And that's exactly how you can make this a bottleneck, because what you're going to do is you're going to add penalties and noise to the various stages of the construction and reconstruction. You're going to try and see that you can still reconstruct things under noise. As a matter of fact, training with input noise, dropout, weight decay, all those things are actually quite effective mechanisms of keeping your capacity at bay. So that's why there is really a bottleneck in terms of the information transfer. Because it's not just that you can store infinite information in a floating point number. You basically apply a sufficient amount of noise that the information that you can convey through a floating point number is limited. Okay. So here's a cool thing that you could do with this. And for lack of a better word, and because it doesn't really have a nice name, I'm just going to call it synesthesia. I guess you guys all know what synesthesia is. If you can put colors on numbers, or you can taste music, or basically when senses that shouldn't be the same actually overflow and blend into each other. And effectively, that's probably the same idea behind a lot of those recent papers that sound like the deep network understands and it has intelligence and whatever. But basically what it does is you take data from two different types of sources. For instance, it could be English and Klingon. It could be images and captions. It could be natural language queries and SQL queries. It could be movies and actions. It could actually be MRI activity and then the text that was read to the patients while they were being observed. And the latter actually has been done. So this is a cool paper that Tom Mitchell and Leila Webe wrote recently. So basically, take stuff where you assume that there must be some correlation somewhere, somehow. And it's really as vague as that. And now, what you're basically going to try and do is, you're going to try and build an autoencoder, if you will. So you're going to try and build an autoencoder, let's say, for the first source. You're going to try and build an autoencoder for the second source. And what you're going to require is that at the innermost representation level, both autoencoders use the same representation. So, of course, you need at least some pairs where this is nicely matched up, but you can actually train your autoencoder on a larger set of data, because maybe you have more sets of captions and more images than you have paired sets. But you need to make sure that they both operate on the same representation. That's really key. If you only want to go from one domain to the other, let's say from English to Klingon, you don't really need an autoencoder for English, but you need at least a generative procedure for Klingon that reconstructs Klingon from Klingon, right? So the example that I have here on the right is basically you have, for language 1, I have some word embeddings. I then do something interesting to get sentence embeddings. So there's actually a nice ACL tutorial from last year by a guy called Nel Kalchenbrenner. And so look through his slides. I mean, it's about 160, 170 slides. Fairly detailed slide deck on vector representations in NLP. And you'll find a lot more of this kind in there. And so basically what you do is you need, at the very least, for language 2, a mechanism of going forward and backwards between the embedding and the original language. And then you basically go and minimize the distance between the pairs. And, well, if you were to do this naively, you could just go and map everything onto smaller and smaller scales. So all the distances would be, trivially small. And that's, of course, not the idea. You want to make sure that wrong pairs are not close together. So this gives you something that's more like a large margin loss. So you do remember our large margin classifier, and this is really doing the same thing here. So what we use as a penalty is, let's say I want to make sure that I match A and B really nicely. So I want this to be small. However, I want to make sure that for some imposter n, the distance between A and the imposter is large, right? So therefore, I want this, so the negative distance, I want this to be large, I want this to be small. And because if this is large, then this is not good, right? I want this term, of course, to be small, right? Because the distance should be small, the negative this distance should be large, so minus that will be small. And I want to make sure that there's at least a reasonable margin of separation between those two things. So let's say here is A, and let's say here's B. And they have some distance, right? Then I want to make sure that, if this is a set of possible B's with the same distance, that all the other ends are at least margin far apart. So this is margin. So everything else should be out here. So the idea is, therefore, that if I go and try to find a related sequence, that one's just way closer to what I'm searching for than all the incorrect answers. Now, unfortunately, that's a little bit hard to optimize over, because that's like finding the needle in the haystack. Let's say I have, in pairs, then, in other words, 2n observations, and there's only one closest guy to it, and all the other 2n minus 2 candidates are, of course, wrong, so really needle in the haystack. So what you do is, when you optimize over it, you basically pick random pairs or maybe weigh it a little bit according to the distance, because doing a maximum search at each step is really expensive. Okay. And you can write papers about different heuristics of how to do that. Okay. A really important thing is that data sets can often be too small. So you would think, ImageNet, it's a terabyte. If you crawl it raw, is big. Well, no, not really, because it doesn't include all the camera perspective transformations and whatever other things that you could be doing. And so you may actually very well want to augment your data set based on prior knowledge that you have of what you would expect to see. And For instance, with text, I can have typos. So if I added a typo here to this text, you would still be able to understand it just as well as before. Only if I started adding lots of typos, would it get difficult for you to understand the meaning of the text. So even though those objects are not identical, they mean the same. And in the same way, I would expect that anything that uses this as input should actually generate the same output. Likewise, if I take a picture of me, and I take a picture of me maybe overexposed or maybe in the shadow, then this is still me. So now for the camera, this looks very, very different. So if you watch it in the video, you'll see it. You can actually perform some of those transformations directly on the images. That has actually led to really, really good results, both for speech recognitions and images, but it can be ridiculously expensive. So this is actually quite similar to what Bernhard Schellkopf did about 20 years ago with virtual support vectors. And it's also very similar to what Chris Bishop did in 95, so really 20 years ago, when he basically discussed training with input noise and regularization. It's a very cute paper. The analysis is fairly straightforward. Basically, if you have a smoothly differentiable function, then training with input noise is the same thing as just imposing a penalty on the on how non-smooth the function is there. It's very straightforward analysis, but very cute. And what it does is it basically, therefore, requires our estimators to be not too sensitive to local changes in the parameters. And yeah, I mean, if you think about it, everybody recognizes these cards, right? King of Hearts. No, but, well, it's the king, but whatever. The point is, these cards don't really change if I transform them, but for a computer vision system, they would be very different. So you actually want to be able to, directly learn this. Okay. We're going to revisit this a little bit further, but this sort of kind of summarizes things that we could try to learn. Okay, any questions so far? Okay, good. So now we get to optimization, and this is, well, unfortunately not as well established an area in deep learning as it probably should be. As in, yes, there are general rules, but there is no very nice, deep, thorough, comprehensive analysis that tells you a priori, well, for this problem you should be doing such and such. It's gotten to the point where sometimes parameter adjustment and so on itself is done by either Bayesian optimization or then something else. So you get to this nice meta scenario where you have a deep learner using deep learning to train the deep learning training algorithm. Duh. Okay. Let's go through and this is basically, yeah. You basically want to tune your parameters automatically if you can get away with that. So there are two libraries for that. One is called Spearmint, the other one's called Mo. If you use commercial code, use Mo. If you use it just academically, Spearmint's also an option. So here's the basic idea. Well, in stochastic gradient descent, you just go and take your parameters, you compute the gradient, and then you update it a little bit, right? And so now you have a couple of issues that you need to address. Well, for instance, how large a step should I take? Should I adjust each parameter individually for that? Should I take larger mini batches? And mini batches simply means that I'm going to take several observations at once and then take an update step after I've seen some of them. Should I use a momentum? And the reason why you may want to use a momentum is if you have an objective function that looks like so, right? Then, by just squinting at that, you realize, well, you should be going down here, you should be going down there. But if you look at your local gradients, they will look anything but that. So it's probably a good idea to average over past gradients. So mini batch and momentum serve somewhat comparable roles, but not quite the same, because averaging over the data may not exactly get rid of these non-smoothness parts here. So that's why momentum is sometimes good. There's a cool paper here which goes through a lot of different ones of these update tricks. So yeah. So mini batch is the first thing that you may want to look at. Basically, what you want to do is you want to update on more than one observation at once. If you have maybe a couple of billion observations, then taking mini batches of size hundreds to thousands to 10,000s is not a bad idea. It in particular helps when you do things on a GPU, and that's the case because matrix-matrix operations are faster than matrix-vector operations, which in turn are faster than vector-vector operations. So if you have never seen this, pull out Octave or MATLAB and just time what happens if you take vector-vector matrix or matrix-matrix operations, let it run for the same number of floating point operations, same memory footprint, and you'll see that vector-vector is a lot slower. That has a lot to do with cache locality. So don't just take a 10 by 10 matrix because you're not going to see anything. But if you take something that is guaranteed to be larger than the cache of your local machine, you are almost guaranteed to see something very interesting happening. Okay. So on GPUs, the other constraint is, of course, if you have a very large mini batch, then you end up with using up too much memory. So on a GPU, the magic number is somewhere between 64 and 256. That really depends on a little bit which GPU you have. Okay. So then learning rate decay. You could make it constant, but that's really awkward, so just don't. Polynomial decay is probably what you want to use. If you just look at our previous results from convex optimization, if I don't have strong convexity, 1 over square root number of steps was a good number. This is not a bad place to start. A couple of things. Do not reset your learning rate to the original number each time you go through the data again. I know it sounds ridiculous, but I had an intern who once did this. And after 2-3 days of being very worried that his optimization didn't converge, we found that. So don't make that mistake. Also, make sure you don't decrease your learning rate too aggressively. So yes, if you have strong convexity and you know the modulus of strong convexity and all that, order 1 over t learning rate can be okay. In general, it will be too aggressive, and basically you will not actually converge to the optimal solution, but your solver will stall earlier. Again, worked with a student where he ran into exactly that problem. So in case of doubt, start out with something that is a little bit too conservative in terms of how slowly you decrease your learning rate. There are some papers that argue for an exponential decay, but I think it's quite risky. One thing that probably is a good idea is to actually look at the behavior of the objective function, but then it becomes a lot harder to prove things. But there are some recent results where people are starting to look at, well, basically, if my objective function doesn't decrease too much anymore, then maybe reduce the learning rate. The point being, if my learning rate is too large, I basically end up jittering around the current solution and I will not converge further. But of course, also, if I've already cranked down the learning rate so far that I'm really far away from optimality and have no chance of actually getting there, then also nothing will happen. So it's non-trivial. So probably, gamma being maybe 1/2 or Leonbu 2 picks 3/4, I'd probably go with 1/2. Because even if it takes longer, it can make a difference. One important thing is what's called eta grad. Yes?
So with this method, there is no guarantee that we're actually going to reach the local optimal.
Oh, yeah. Yeah. So first, well, okay. So these methods are, so we're solving a non-convex optimization problem. And in a non-convex optimization problem, in general, all bets are off anyway. However, at least you're hoping for a local optimum. And if you have like a 1 over square root iterations learning rate, at least you'll get there. You'll get to a local optimum, but no guarantee on how good it might be. If you have something that's way more aggressive, you don't even have that guarantee anymore. So for an analysis, in that case, have a look, for instance, at our NIPS paper from last year, where we looked at that kind of updates under delays and additional noise and so on, and perturbation. So you can use that directly. Now, a really important thing is essentially preconditioning. So if you think about it, you might have some coordinates that are very sensitive and some coordinates that are not sensitive at all, right? And if I knew that beforehand, everything would be really nice. And if I could compute the second derivative, everything would be nice too. Quite often, I can't quite get that. So what you can do, though, is you can just look at the magnitude of the gradients at previous steps. And so rather than having a given learning rate schedule, you make it adaptive. You basically use the past gradients squared. You aggregate this up, and this will give you some idea of basically how rapidly you should be decreasing the learning rate. So if those gradients are really large, then you're actually going to decrease your learning rate quite rapidly, and you will make only small steps, progress such as not to overshoot. Whereas if your gradients are really tiny, then you will keep your large learning rates for a bit longer. And the idea is you can do that actually on a per coordinate basis. The only catch is that now you need two sets of parameters, one for your actual solution and one as an idea of how large your step sizes should be. But that's usually well worth the trouble. Then you could say, well, maybe what I did initially doesn't matter so much. And so you can do a local version of AdaGrad. And that's again described in the Ranzato et al. Paper that I showed you on the previous slide. So it's basically this term here to calibrate the scale, and this is for the rate. So it just decouples those two things. Whereas this one here will give you, of course, an order 1 over square root t rate. Unless your gradient vanishes even faster. Okay. Any questions so far? Okay. Here's another thing. Momentum. So there are actually two different types of momentum, and the one you should really be looking at is actually this one here. And they look, at first glance, very similar, but they do subtly different things. I've just used a slightly different parameterization because usually for accelerated gradient, that's what people use. Okay. So the idea is basically, in addition to my gradients, I keep a momentum term. And the momentum is basically just a past averaged version of my gradient directions. So what I'm really doing is I have my momentum at time t being the previous momentum, and then I update it a little bit with a gradient. And then my parameters are updated by taking a step in the direction of the gradient, and then I add a little bit of the momentum to it. So this way, even if my gradient may be small, but I still have a large momentum, I keep on going. And this can accelerate things, but of course it can also lead to instabilities. So a rather neat trick is the accelerated gradient method of Nesterov. And what it does is it doesn't look at the gradient at location WT, but it actually already takes a one step look ahead at what happens if I was to take another step forward. It looks at the gradient there to use this to update how far I should be going. So this is a little bit better in terms of overshooting. Because it basically means that if I was to overshoot, but over there the gradient points in the opposite direction, it basically reduces my momentum. So it's a little bit similar to a predictor-corrector method that people use in convex optimization. The cost is, of course, that now you need to compute the gradient, not just where you currently are, but also at one step look ahead. So it basically doubles your computation. Sometimes this can be overall faster in terms of ops count rather than plain momentum. This really depends on your problem. Okay. Why would you care about it? Well, for instance, when you have, all sorts of, nonlinearities and a lot of local minima that are not very meaningful. Okay. A couple of other things you should do is parameter clipping. So both for your gradients and also for your parameters themselves, just impose some upper bound on their value. And this is sometimes for very non-mathematical reasons, such as you're buying a cheap GPU and it overheats and it produces garbage. It sounds funny, but this is a real issue. Because those GPUs, if you write good code, will get very hot. They will run at 90 degrees Celsius and higher. Okay. So, in other words, you're going to run the GPUs at the point where if you probably run them for 1 or 2 years, you're pretty much killing the chip. But by that time, you don't care. Also, numerical instabilities can sometimes lead to these problems. You get some papers where it's almost scary how much hand-holding they do, so you really wonder who's doing the optimization. So where people, at some point when things diverge, just stop the optimization, switch to different optimization algorithm, and it's a little bit trial and error. That said, the results in the end are often quite nice, so there's some justification through the result, but it's not exactly satisfactory in the sense that you don't just have a method where you push a button and you get a nice result. Okay. Really important thing, dropout. This is probably one of the key innovations that have come up. And yes, you can read that paper, and I guess on the 20th of April it would have been a better paper to read. At least some of the text in there is a little bit speculative. Here's what it really does, and you really need to remember that one slide and nothing else. Basically, what you want is you want to prevent over-adaptation of the subsequent layers to very specific parameter values. And you can do that by basically perturbing what gets transmitted to the next layer. And you can do this in multiple ways. The first ones would be just to add some noise, and this is basically the Bishop paper. The second one would be to sparsify the vectors. So in other words, with some probability pi, you keep the coefficient, and usually pi being 1/2 is a pretty good idea. And so when you keep the coefficient, you multiply it by 2. And when you don't keep the coefficient, you just transmit the 0. So this is essentially a randomized procedure, which in expectation will keep the parameters the same, but which basically just adds noise in order to prevent over-adaptation. There are lots of other ways that you could do. So, for instance, you could just take the matrix that you had before and you randomly sparsify the matrix. So a really exciting question is, there's this big industry of essentially matrix and vector sparsifers and compression algorithms, priority sampling, and so on. Well, can you just let all of those algorithms loose on deep networks, and what do you get? And you actually get quite fun results if you do that. So here's just this entire thing in pictures. So this is from Wandley's website. The regular deep network, would have exactly, the inputs. They go through a weight vector. You get some parameters, and then you get the nonlinearity, and it gets transmitted to the next layer. In Dropout, basically, you randomly nuke some of those terms, like let's say this one here, and you just set it to 0 instead. So this prevents exactly that trick where you go and over-encode information in a single coefficient. In Drop Connect, well, what you do there is, if you think about it, this is actually a matrix vector multiplication. Here's the vector, here's the matrix. Then, well, you basically just randomly kill entries in this matrix. And there are plenty of other things that you could do like this. Yes?
So how often do you change what you drop out?
Every time.
Every single pass?
Every single pass, for every single observation, you pick a different random subset. Now, obviously, this is ridiculously wasteful if you first do the matrix vector product and then you decide, well, I didn't need half of it. That hasn't been exploited yet to actually do this a little bit more efficiently in linear algebra. The problem is that sparse linear algebra is a lot more expensive. So you would have to go deep into the dgem-v or dgem kernel basically into your BLAST kernel to actually hardwire Dropout into this. This should actually give you a decent speed up. My guess is probably you'll get a 20 to 30% speed up by just rewriting that kernel. So if somebody wants to do it, you will get the gratitude of pretty much everybody in deep learning if you rewrite that for CUDA. Right? I mean, it's a little bit tedious, but most of the time you just have to go and just decide what to eliminate. Okay. It's not going to be a full 50% improvement just because, well, you have a little bit of overhead in deciding which coefficients not to pick. But yeah, that would be actually kind of a fun undergrad project. Okay. Does it help? Yes, it does quite a bit. And these are some curves of with and without Dropout. And basically, yeah, it's a very, very good regularizer. It's probably one of the more exciting modern regularizers. If you think about it, L2 being the simplest one, which is just shrinkage, L1 being one that's more aggressive towards sparsity, Dropout, which is a procedural prescription. There is by now some amount of math that suggests what Dropout might possibly do, but I don't think it's a fully solved problem yet. But yes, it does help quite a bit. Okay. So that concludes the optimization part. Now we'll actually get to one of the most fun and actually most research-wise active areas of deep learning, namely the issue of memory. And this is where a lot of the claims of intelligence come from. Any questions so far about the optimization part? Okay. And there's actually a really cool tutorial by Alex Graves. Just look for this guy. I think there's an actor with the same name, but you want to get the scientist. And one of his tutorials is basically sequence generation with RNNs. I think that's the title. He has very nice slides that go with that. So look at them. As a matter of fact, you guys saw some of the slides in the first presentation where they just copied the slides. Okay, so the simplest thing is you could use IID data, and, well, that's kind of nice. But most of the data isn't really IID, so sequence annotation for tagging, parsing, sequence generation for translation, for document summarization, image annotation, context extraction, all of those things will actually require you to operate on non-IID data. Well, we learned one way of dealing with this, namely through dynamic programming. And dynamic programming is kind of nice because you don't need a lot of intelligence locally, as long as then through forward, backwards, you can actually resolve a lot of ambiguities. The idea behind a lot of those recurrent models that I'm going to show you here is actually different insofar as it assumes that, well, while yes, that forward-backward information would carry a lot more value, in many cases, a suitable nonlinearity in just forward prediction will do a good job. I mean, yes, this is a gross oversimplification because by now people actually have looked at bidirectional LSTMs and similar things. But largely, the idea is really that you can do a lot without dynamic programming if you can just learn the right forward predictor. Okay. So, here's a simple thing that you could do. You could use an autoregressive model. So quite often in the stock market, you might do that. You basically would say, well, x plus 1, so the value of the stock or of several stocks at time t plus 1 is some function of, whatever I had at time t up to time t minus tau. So the idea is basically that all that there is to know for me to predict the next thing is entirely encoded in the last, let's say 10 or 15 steps. Which is kind of nice if all these decisions really are that local. But for instance, if I additionally told you, well, right now we are in an inflation, or let's say we have a depression, or let's say this is a bull's market. So if I told you all this side information, you ought to be able to do a lot better than just in the simple autoregressive model. So in other words, the idea is you would often want to have a small amount of additional hidden state that captures those long-range correlations beyond just the simple autoregressive model. The example that I think motivated the design of the LSTM, so yeah, wonderful name, long short-term memory, is the XOR problem. So if I gave you a sequence and in the end you had to tell me whether the XOR of the sequence is 1 or 0, then you would actually need to be able to aggregate all the state of what you've consumed right from the beginning in order to come up with the answer in the end. Right? So any window of size tau would be utterly worthless because XOR is not a local operation. XOR operates on the entire sequence. Now, you can actually do this by basically adding a latent state. So you would basically assume that in addition to x, we have some variables z, and they are not observed. So this is similar to what we would have in an HMM, a hidden Markov model. And just in the same way as x is propagated through time, we also propagate the latent state. And that's really at the heart of many of those memory type models. Right? And now the specific design of how Z looks like, this is where a lot of those algorithms differ. Right. So we're going to look at 2-3 specific variants today, but there's a lot more going on right now, and you should really read up on those papers. Okay. Any questions so far on the conceptual part? Right. So this is just in pictures of what's going on. The top line is basically just an autoregressive model. Actually, I should have, added those arcs. Right. This would make it. Right. Now, in an LSTM, you would basically, or just a latent state model, you would basically have this additional latent state, and that gets propagated in the same way. Okay. Now, here's a problem. If you run backprop through this, so you basically end up doing backprop through time because you need to backprop through the entire sequence of observations, it can get kind of messy to try to actually, for instance, in the XOR problem, get the information through up to the very end. And part of the reason why it gets messy is that, if your gradients have, if your Jacobi matrix has the largest singular value less than 1, then this will converge to 0. If it's larger than 1, everything will blow up, and you don't want that either. So it's really hard to exactly keep the gradients from either vanishing or blowing up. That makes it really hard and painful to train. So what Hochreiter and Schmidhuber about, let's see, this would be about 24, 25 years ago did, this was actually, I think, a master's thesis of Sepp Hochreiter at the time. The guy basically said, well, let's go and design something that behaves like a memory cell in a circuit. And let's use this very specific, carefully crafted mechanism to deal with the updates. And that's actually become the template for a lot of those approaches. And we're going to look at the specific dynamics in a moment. The specifics aren't super important right now for the conceptual understanding, but here's basically what happens. You assume that this Z is essentially a memory cell. And this memory cell, at each step, so this is clocked, is fed with some input, right? And it basically uses its current state and the input to decide by how much it should actually change its state. It uses its current state and the input also to decide by how much it should forget its current state. It uses its previous output and the current state and so on to decide how much it should actually output. And this is then used for subsequent things. So basically, I have 3 operations: input, reset, and output. And each of those 3 things are gated. Right? So with those 3 operations explicitly parameterized, you can actually keep the gradients from vanishing quite that much, but it's a little bit more costly to implement. Okay, so here are the update operations. I basically have a couple of gating functions, I, F, and O. So I is the input, F is the forgetting, and O is the output. They are all given by some nonlinearity applied to, well, the current state. The output is also depends on the, well, state of the network. And then what I do is I basically generate my new state as a linear combination of the input, right, suitably adjusted. This is the input, suitably adjusted, gated with the input gating, plus then a leaky average, which is basically just my previous hidden state, well, gated with some forgetting function. And then the state that I emit is the state HT, which is just output gate times and then some other nonlinearity of my hidden state. Whether you use a tang or whether you use something else is probably a little bit less important. The overall construction is reasonably resilient to modification, so people have sometimes removed pieces to make it, well, perform faster on their specific architecture. Yeah, I mean, it basically has the 3 components that you need. You need an input, you need a latent state, you need an output, and you need then corresponding gating operations for what you do with your latent state. Right? And that actually can be used to store information about past observations rather nicely. Okay. For instance, you could use this for sequence generation, where you just have your LSTM state. And by the way, this need not necessarily be a scalar. You could have an entire vector of those things. And these operations might be applied on a per coordinate basis or maybe overall. And so sequence generation then would be to use the previous observed state and the hidden state to generate the next thing. You could also use this to classify a sequence. So you basically go and use the inputs to generate this latent representation, which takes previous information into account. So this would be useful, for instance, if you want to deal with double negation. Like, this was not a bad movie. And if you want to have this, then you basically not flips things, bad flips things, and then movie, right? So to deal with that kind of context, it helps if you can capture state. And so this is kind of useful. You can actually then go and group things into layers. And then you get overall dynamics at different scales. So that's quite effective. A rather cute example is this one here. This was a NIPS paper from last year. What they did was amazingly simple. So they basically took an LSTM and they fed a sequence of, well, let's say, English text into it. And then they read a sequence of French text out of it. Okay, so how does that work, right? Sounds kind of magic. So basically, what you do is you optimize, because you can use it as a generative process, for the log likelihood of corresponding words being emitted. And before that, when you insert each word, well, basically, this updates the state of the LSTM. And this is not just a single LSTM. They use probably, I think, 3,000-4,000 cells or more, right? So this is, it requires a decent amount of GPUs. And what you get is a couple of things that are kind of cute. So first of all, you actually get a really good natural language translation model. And they were, let's just say, surprised how well it worked. So fun thing is you basically need to input the sequence, and then you need to input an end symbol to tell the network that now please start emitting things. And what it does is basically at this time here, this model actually has a fairly good representation of what you fed into the model learned as its representation. And so what they then did is they actually, just ran PCA on a couple of related sentences and they plotted them. And here's what you get. And you get, things that are, distinctly different, right? So John respects Mary, Mary respects John. Things that are closer, right? Mary admires John or Mary's in love with John. Right? And so you actually get quite meaningful similarities between sentences through the latent representation. Well, you better have that if you want to be able to translate well. There's an obvious catch with this. This does not work quite so amazingly well on long sentences, right? Because what you're basically trying to do is you're trying to input the entire long sentence that I'm now going to speak without any end, and I'm just going to continue talking in the same way without any point and comma and whatever for a long time. You're going to put all of this into a latent state. Well, forget about it, right? What you can actually do is you can basically have a similar mechanism where you have a window that moves over the input sequence and then uses this to emit the corresponding output. So it's a nice model that Kyung-Yoon Cho and co-workers came up with that actually works a little bit better. Here's another couple of examples of pretty results. Like in the garden, I gave her a card, or she was given a card by me in the garden. Means rather similar things. But then I was given a card by her in the garden means something quite different, and it's further apart. Does the deep network understand what it's doing? Well, heck no, but it's a fairly useful representation. Okay. So this brings us back to the model that I showed you before. What you could do is, instead of just those simple word embeddings, you could basically go and, just use contrastive estimation to get similarity between paired representations. So for instance, you would have one generative model for one language, another generative model for another language. And so if you wanted to have a universal translation system, you would basically translate all possible text into the same representation for all the languages. And so then if you wanted to have a new language, you would just need to attach this representation to another generative model, which may or may not work. Okay. I think that's kind of all that I would need to say about this. Yeah, there's a lot more in that research direction. So the link bait equivalent of a paper title is this neural Turing machine. Well, sounds cool, right? It's actually kind of nice in the idea that you basically have a slightly more dynamic amount of memory. So rather than hard coding the number of LSTM cells, you basically have a tape, and you operate on the tape, and you traverse it, and you can go forward and backwards and do corresponding readout operations. So this is by Alex Graves and coworkers. Then Jason Weston and coworkers, they looked at what they call memory networks, which is a limited subset of this. But limiting things also means it's a little bit easier to train. You then can use attention models. So this is also quite neat, where you basically say, well, my original data is a pretty good substitute for actually having a tape, where then, for instance, if I have a sequence, I would have a pointer to parts of that sequence where you actually go and read things out. And then you need to define what it means to go forward or backwards within that sequence. The advantage is that this way, if somebody just keeps on talking without end and doesn't finish his sentence for a very long time, I can actually have a pointer that moves along this, and I don't have to train a specific model for people rambling, right? So this is actually, I think, at the moment, the most exciting area of deep networks. How do you actually make all of this work? And we don't really have a lot of time to go into details here. So all I did is just, get you a list of some things that you could look at. So one of the first things probably to start with is Caffe. It's pretty neat for convolutional models, and NVIDIA loves it. And NVIDIA will happily talk about that in demos. And if you have order 1 GPUs on a single machine, and if you don't try doing a lot of memory type models and just mostly convolutions, this is a good idea. Furthermore, they got one thing pretty right, which is namely their layer description, and some of the other models actually can use Caffe config files to implement the same network. Okay. So then there's Torch, which I think is more efficient and way more general. So provided that you can put up with Lua, it's actually not bad. And the folks at Facebook and also to some extent at Google really like it a lot. They like it so much that they're actually working on this. The extent to which you can probably find out if you do an internship either in London at DeepMind or at Facebook at the FAIR team. And in both of those cases, you'll see that it's very popular there. Then there's something called Theano, which is in its intention actually pretty good. Namely, you would go and turn, you would pick some domain-specific language. In this case, they actually pick some Python with a couple of constraints, and you then compile it directly into code. And so the idea is to let the compiler do a lot of things that you would otherwise have to do by hand. And while this works nicely on paper, the compiler isn't quite so amazing, so Torch is actually faster. Something that's really cool is actually Minerva. So what you do is, similar to Torch, you actually go and specify your model, and then you have a optimizer lay out the computations on a machine, and that means basically multiple GPUs, maybe a CPU. So in other words, it's actually doing really nice scheduling of small computational kernels over a large amount of hardware. This is really nice, and it works very well if your computational kernels are big enough. If they're very, very small, you run into massive performance problems. So it basically tries to micromanage task execution on a GPU. This will get fixed, but it's not fixed yet. CXXNet is probably a much more lightweight and clean version than what Caffe has, but it's a little bit of a subset of it. It does take Caffe config files just like Minerva. Those two projects are actually merging. Note this thing here. And note this thing here. Distributed machine learning in C. So this is actually all starting to merge and gel with the parameter server, which by now has bindings to Minerva, Caffe, CXXNet, and so on. And so within, I guess, a matter of months, maybe half a year, there will be a very, very scalable, distributed, fault-tolerant library for deep learning available. And right now, I think only 2-3 places in the world have such a system, and it'll be open source after that. So start using it, basically. I want to conclude with this. Well, thanks for sticking with the class until the end. Next week are presentations. The week thereafter is an exam. The exam is going to be of a very similar form as the midterm. So in other words, same length, same relative importance. So I don't think it's a good idea to have like this one big monster of a final. Just to really make it clear, you can bring as much paper means you can bring printed paper. I think somebody brought a big stack of white paper. He still passed. He passed quite well because he was a smart guy, but yes, you can bring paper. It should be not too hard. I mean, other than that, yeah, well, good luck for the presentations. One thing that's important is your project summaries. You must not be late. Here's why. Because we need to actually provide grades for the entire class, right? And for that, the TAs need to grade things. Now, if you submit your summaries, 1 or 2 days before the grades are due, then the TAs will have maybe 12 hours to grade your summary. That doesn't make for a lot of time to give you a good grading, right? Doesn't make for a lot of time to give you good feedback. So you're basically really screwing over the poor TAs because they now need to drop everything else like conference deadlines and whatever and just, grade your stuff. So don't do it. As a matter of fact, there's a penalty for it insofar as you'll just get less points if you're late. So please don't do it. But I just want to explain why it's important that we do this, because the university requires me to forward your grades to input the grades into the system, and it needs to be done by a certain day. And if it's not done, then it's a problem for the university. So this is why we have that constraint. Otherwise, I'd be perfectly okay to give you more slack, but well, there are deadlines that are beyond my control. So thanks a lot for making it through the class, and I hope you got something useful out of it. Questions? Yes. So there's a decent description of that on the website, but basically, yes, a paper would be just perfect, right? Now, if you don't have a paper, I mean, essentially the instructions are along the lines of stuff you should probably write in a paper. As in, you should explain why on earth you're doing this, what it's good for, a little bit, what's been done before. So in other words, to make it a little bit easier to assess what actually a novel contribution is. So in other words, don't just go and copy existing slides, content and other stuff without giving proper credit. That's not cool. It should obviously not be something where we really should be grading your advisor, right? So, but I guess it's too late by now if that happened. Acknowledge the people who helped you. That's also just out of courtesy and politeness. It's something that you always do. And unless you have a really strong reason, the videos will be up online publicly, right? So practice giving the presentations beforehand. So they will be raw, unedited, and go online like this, right? So it's the same thing for me. I mean, if I do say something stupid, right, like before that, mistaking, the ace of spades or whatever, well, everybody gets to laugh about it online, right? So do better than me. Okay, good. So thanks a lot. And sorry, one question.
Do you have like a length guideline for the paper?
Yes, I think it's online. I forgot exactly what it was. It was probably 6 pages, double column, something along this line. So there's an upper limit. I don't necessarily have a strict lower limit, but if you just write Mary had a little lamb, you're probably not going to get a very good score for it, basically. So the upper limit is mostly as a, protection for the TAs, because somebody has to read the stuff. And if you submit War and Peace, then you cannot expect the TA to read War and Peace. And it also means that you will have to get to the point in a reasonably brief amount of space and time. So there's enough space for you to actually describe what you're doing, and not enough space to ramble endlessly. Any other questions? Yes? Okay, you sign up. Basically request, and the sooner you ask for a specific day, namely Monday or Wednesday, the sooner we can confirm. Once one of the 2 days is full, you just get the other day. Yeah, by email to the TAs. Okay, good. So then thanks, and see you next week. And then you'll do the lecturing and I will listen.